The NBA is considered the most popular basketball league in the entire world. Millions of viewers from many countries tune in with a single question in mind: who will win? Several betting sites and game commentators try to make predictions on the final outcome, and they're fairly accurate. The objective of this project is to build our own expert to do the same thing, but using machine learning.
Yeah, all right. So the first method that we sort of explored to predict the outcome of games was to take the results of each game. For each game that is played in a particular season, there are certain statistics associated with each team that plays in that season. And also for each game, we have the scores of each game, like basically how many points each team scored. So basically taking both of these data sets, the monthly average statistics of a team and the outcomes of each game, we were able to sort of create a very extensive data set for a particular season. And so the way we obtained this data was using popular web scraping Python libraries like Selenium and Beautiful Soup. We took the data from popular basketball statistic websites like basketballreference.com and the official NBA stats website, and sort of taking these monthly average statistics and taking the outcomes of games, we sort of merge these data sets together, and we have a pretty extensive data set to train our model on. Next, we performed exploratory data analysis, basically to look at the correlation between data, um, to sort of remove redundant variables and just to view sort of how our data is related to our outcome variable. And so this heat map that is shown is basically the correlation coefficient of every or the most correlated attributes with the outcome variable, which is the home win attribute. So after removing redundant features, we started training our model using different methods. We tried using the normal logistic regression. We tried using the ridge classifier and the lasso classifier. So the ridge classifier is what gave us a pretty good result. And as you can see here, the cross validation score is reaching nearly 73%. And so using this model, we were able to predict the outcomes of NBA games with approximately 73% accuracy. So this is how we used the results of games to predict the outcome of NBA games. Another method that we sort of looked at to predict the outcomes is using box scores. So the results of games give team-wide statistics. However, the box scores give detailed statistics about each player. And so this player statistics are not only for the 5 people who are playing on the court at any time. Usually there are more than like 9 or 10 people who are on the lineup for a team, and so box scores provide detailed statistics about each player on the lineup. So using these statistics, Keshav Puranmalka proposes in his paper to use these features as well as creating novel features to more accurately predict the skills of a player. So box scores only measure what happens on the court, but there are other factors that also affect how a player can play. Some factors might include the number of rest days that the player has had between two games, or the geographical distance that the player had to travel between one game. That might have a sort of a positive or negative outcome on how that player will play. So once we have the statistics about each player, we basically have a kind of a performance metric for each player. And if we had to pair up 5 players and sort of play them in an imaginary game against 5 other players using this performance metric, we can basically see how well these players would play together. So using feature selection algorithms and support vector machines, the paper was able to sort of get results that are 2 to 3% more accurate than publicly available state-of-the-art predictors. These state-of-the-art predictors are used in popular betting sites and fantasy basketball leagues. And this paper was produced. This paper proved to be 2 to 3% more accurate. So this is how we use box scores to predict the outcomes of NBA games.
Since basketball is a team game, we try to look at player chemistry to predict the outcome of the games. The motivation of our model is to understand the role this player chemistry or synergy may play in predicting game outcomes and providing a quantitative prediction of chemistry between players. The input for our model will be the identity of the players on each team for a given game. We'll then use logistic regression with a linear model and a quadratic model to output a prediction on which team will win the match. We'll also provide a comparison using a multi-layered perceptron neural network. So now we take a look at the learned parameters of the quadratic model, which will give us the quantitative parameters to compare the chemistry between the players. The feature vector for each team would have a total length of the number of the players. We would have 1 in the positions corresponding to the players in the team and zeros elsewhere. Using this as the input to our quadratic model, we get two matrices S and A. These are very important matrices because the diagonal elements of S give an indicator of the player's individual skill. The off diagonal elements of S give an indicator of how much two players as a teammate would contribute positively to the win percentage of their team. The off diagonal elements of the matrix A give an indicator of the difference in the player's contribution to their team's winning chance when they are on the opposing teams. These are very important parameters because using this we can calculate how two players I and j would fit together. If the value of s of sij is high, then the players I and j would be good together, and if and aij is low, then also they would be good together. But vice versa, if the value of sij is low and aij is high, then the players won't fit together well. Now, this work has a lot of potential because it can effectively predict which players should be paired together. It can predict successful transfers and trades, but there are some drawbacks because we have to include age as a factor. Also, this model doesn't account for any new players. Nevertheless, it has a lot of scope and it can be explored further.
Another way which we saw was using positive and negative synergies. The paper which we followed gives us a skill plus minus framework which is used to measure the synergies within basketball lineups. It can also give us roster dependent rankings of free agents and also generate multiple trades. So for this, we took into consideration ball handling, rebounding, and scoring for the skills, both offensive and defensive. So how it goes is, first we try to find the probability of any event occurring by using this formula. So I'll just give an example. Let's say the probability of a steal by Rondo is given as 6.4% if Rondo's team has the ball, and it's given as 9% if Rondo's opponent has the ball. So it says that Rondo is a good point guard in terms of defense. So using these probabilities, what we do is we can get multiple events and we can find the flow of these events. So how individual player ratings is calculated? What we do is we choose a player and consider a skill. All the other skills are given replacement level stats, which is basically the stat of an average player. All his teammates are also given replacement level skills, and also the opponent, everyone in the opponent team. So by going through the flow of events, we find the score, and this score will be the individual rating of the player. So how we find the synergy is that if we combine two people with different skills, we do the same thing. We generate we get the final score, and the point differential between the individual and the combined scores will be the synergies for that player. So by this, we can actually generate multiple combinations of players, and you can find a team which has the maximum synergy. Another way which we used was generating multiple lineups. So in this, we also consider the salary of a player. So in that, one method which we used was LightGBM. So LightGBM is a gradient boosting framework which uses a tree-based learning algorithm. How it's different from the other gradient boosting algorithms is that it's quite fast and it can handle large size of data. In our case, our data set had about 1.2 lakh records, which made LightGBM more suitable. Another advantage it gives is that it splits the tree leaf-wise and gives us the best fit. Whereas in the case of other boosting algorithms, we split the tree depth-wise or level-wise. So by splitting it leaf-wise, we can actually reduce the loss on the level-wise algorithm and get better results.
Also, we used Bayesian optimization. So what is Bayesian optimization? It's a probabilistic model-based approach for finding minimum of any function that returns a real valued matrix. It's very effective for solving real-world problems, and it's often used with LightGBM. Bayesian optimization utilizes a Bayesian technique of setting a prior belief over an objective function and then combining it with the present evidence to get a posterior function. hyperparameter tuning using Bayesian optimization of machine learning models is much more effective than grid search and random search. Therefore, it is very popular and it has a lot of uses, and it has better performance on test data and takes a very less time for optimizations.
We now wanted to see if deep learning can give us some better insight into this problem, so we implemented 3 neural networks using TensorFlow. These models were similar in the sense that they all used the ReLU activation function in the hidden layers, computed loss using root mean square, and minimized it using the Adam optimizer. Now, the first model was the least dense, having just 2 hidden layers with 64 and 32 units in each. The model did okay on training set, but started overfitting after the first few epochs, since the validation error began to diverge from the training error. The second model had 3 layers with 64, 128, and 32 units, and also used dropout regularization. It was comparatively better since it did not show a significant increase in validation error as training went on, and also had a low training error. The third model was the most dense, with 3 layers having 128, 256, and 64 units. It also had a dropout layer. Although the increase in density should have allowed this model to learn more complex features, it ended up overfitting because it learned features too specific to the training set. Finally, we understood that even though the volume of data we had might have been too less to obtain good results through deep learning, it still showed a slight improvement compared to the boosting models.
We then try to solve the problem of lineup optimization, and to this we use genetic algorithms. Genetic algorithms are a search-based optimization technique, and they derive their inspiration from the genetic phenomenon of mutation and recombination. So basically, what the whole framework does is that there is a set of random lineups that are chosen as the first generation, and then based on the fitness levels of these random lineups, these lineups are allowed to mate and produce individuals while being subject to mutation and recombination, which leads to a next generation of lineups. And then these randomized solutions, these randomized lineups, are then converted into optimal solutions, and hence the problem of lineup optimization is solved. Yeah, another area of study that we considered was considering expert opinions of basketball games into our predictions. So, in conventional machine learning tasks, predictions are mainly based on data that are very reliable, and we disregard data that are not very reliable. For example, the opinions of people, experts, and poll outcomes, etc. Even though in general life we consider these experts' opinions as very important while making decisions, it's not very well explored in machine learning, but there is a lot of research going on into it lately. So to use this expert opinion in NBA prediction, we first need to rank these experts based on the previous predictions they've made. And once these experts are ranked, we need to weigh their opinions based on the reliability that we derive from their ranking. And now that we have these weights, we need to train an ensemble of expert classifiers, which will give us the best, which will give us a result that is better than all of them individually. So one of the potential issues with this is that it is difficult to get the results of each game and map it to uh, the the expert's opinion, because the text search domain is very large, and they don't go hand in hand, because the expert's opinion comes in days before the game, and it's not very easy to map it. So we can use an unsupervised method to go along with this. So Parisi et al. In 2014 described a way to rank classifiers and then build a meta classifier in an unsupervised manner. And how it works is, if you have M classifiers, and in our case there are M experts who are giving predictions for D matches, they use a spectral method to rank these M classifiers on their reliability. And then they use these rankings with the with expectation maximization procedure to get the maximum likelihood estimate, and they rank and create an ensemble meta classifier of experts, which can give us the best outcome. Taking one step further, Shyam et al. In 2016 use deep unsupervised learning approaches using restricted Boltzmann machine-based deep neural networks to create the same ensemble of predictors. Now, while the approach they took is quite similar, they first proved that the previous model, that is the Parisi et al. Model, could directly be represented by a restricted Boltzmann machine with one hidden layer. And then while adding on more layers to the RBM to create an RBM based DNN, they realized that this can form an unsupervised metaclassifier that can also deal with conditional dependence. Conditional dependence in this case is that we do not require the errors made by the experts to be completely independent of each other, which is kind of what happens in real life. So, even though using expert opinions for game predictions is not a very widely studied or commonly used topic, there is a lot of scope and there are a lot of unsupervised methods that have come up which can help us. Solve this problem, even though the data sets are not very easily available. To give an overview of everything that we've done, is that we first consider the basic model, that is, the team is one single unit, and the data used to train was the team statistics and not the players. As it is obvious, there is a flaw in it because the teams are always reformed in different seasons, and the statistics of different seasons are not they're not related to each other. So then we use a model that uses the player information, and this basically quantifies the synergy between the players and also the dominance they assert over their adversary. Up to this point, this was everything that we did was towards predicting the entire game outcome, and then we moved towards predicting the short-term events that occur during the game, such as turnovers, steals, and rebounds. So we looked at box scores of the game. So box scores of the game do not just contain information about each of these events, but also the players who are present on court when each of these events occurred. And this can help us to make predictions not only on the outcome of the whole game, but also on the intermediate events that occur in it. Finally, we also look at models to build the teams that have the best chance at beating a given opponent. And this is similar to how fantasy basketball leagues are formed. And we use multiple models for these, as we explained in our video earlier. We also looked at using expert predictions for fine-tuning our final outcomes, and yeah, that's all the things we explored. Thank you so much for watching this video.